Hi everyone. Let me thank the organizers for giving me the opportunity to speak here. I'm a postdoc at and my talk is on integral combinations of characters of representations of finite groups, which we can find from two-dimensional. So let me start with the motivation. So QFTs or quantum field theories have given us a lot of insight into many areas of mathematics, and also allowed us to help us define new mathematical structures. But quantum field theories in general are complicated objects. If we have some partition function of a physical theory, that theory depends on a lot of data that you have, the metric on the manifold, the fields that you have in manifold. And even if you assume that the field theory depends only on, like, let's say, the area of the manifold, the vector space associated to the Hilbert space of the theory will be infinite dimensional, and you have to deal with problems in analysis to rigorously define the QFT. But I will look at special classes of QFTs which are topological, for which the Hilbert spaces or vector spaces are finite dimensional. And in particular, I will look at, in some sense, the simplest of the TQFTs, which can be obtained from a finite group. So these are the diagram-Witten theories. And I will essentially, the idea is to use these quantum field theories, which are defined using a finite group, and use properties of these quantum field theories to understand about some group theory, or try to reinterpret problems in group theory in a physical way using these quantum field theories. So that's the idea. And this is based on, so let me go back and say that this is based on upcoming work with Adrian Pedalero and Sanjay Ram Ghulam from Queen Mary, University of London. And it's a continuation of these works that Sanjay Ram Ghulam and collaborators worked on. So let me go to the So this will be about two-dimensional TQFTs. So 2D TQFTs assigns a vector space, let's call it A, to the circle. And when we have cobordisms, it associates linear maps on this vector space. And the pair of pans, the existence of these cobordisms associates a multiplication, gives us a multiplication on this vector space and a non-degenerate value of 1. And you can show that this vector space is actually a Frobenius algebra. So we have a Frobenius algebra which gives us 2D TQFT. And this Frobenius algebra will be more specific in my talk. So the Frobenius algebra that we are interested in is actually related to a finite group. So I'll be specifically looking at TQFTs that comes from the center of the group algebra. The center of the group algebra, we can think of it as a commutative Frobenius algebra. And this is the algebra that the TQFT assigns to the circle. And for this TQFT, there's a partition function. So given a genus G two-dimensional manifold, the TQFT gives us a complex number. In general, a complex number on the defined for the manifold. And for this theory, the genus G 2D manifold Mg, we get a number which is this sum over these. So dr is the dimension of representation R, and we have the sum. And we see that this is actually an integer for G greater than or equal to 1 or integral rational. Now, we are also interested in some manifolds with boundaries. So we have some two-dimensional manifold with n boundaries. And the boundaries are labeled by some conjugacy clauses. So you can think of the center of the group algebra having a basis labeled by conjugacy clauses. And these conjugacy clauses give some decoration for the boundary. And for such a manifold, we get a partition function, which is a generalization of this with these characters. So these would be the main objects that we use. Now, yeah, so this number here is a rational number. This comes from the definition. One way to say this is just use the definition of partition function. So, for example, Fukuma Hosono-Kawai defined this partition function using a triangulation of the manifold and gives us an explicit prescription on how to find this partition function. And that prescription tells us that it's a rational number. Or you can use a Galois group and act on this expression to show that it's a rational number. I'll come back to the Galois group perspective soon. So we know that if we take a sum over representations, irreducible representations of a character, this is a column sum in the sense that you just look at the character table, representations giving you the rows, and this is like a sum along a column character table, and this is an integer, which we know from various reasons. For example, orthogonality of factors. Now the question is, can we give a QFT argument for this, more a field theory argument for this? And to see this, we look at a particular partition function. So we look at this partition function, which is defined for a genus G manifold with one boundary. And we label that boundary with some conjugacy class C. So this is a partition function that we're interested in. So we start with this expression here, which is a sum over all irreducible representations. And we split that sum into two parts. One is a sum over R prime. And for every R prime, we define a set dr prime, and there's another sum. So the definition of the set dr prime is this. So once we choose an R prime, we sum over all representations with the same dimension as R prime. So the first sum is over representations with distinct dimension. And for every such representation, you have another sum, which sums over all representations with that dimension. So this is just a level set splitting of this total sum. What the splitting allows us to do is rewrite this expression in the following way. So we choose genus, which is G, from 1 to K, where K is the number of irreducible representations with distinct dimensions. So that is the range of G. And once we have the splitting, we can think of this expression in the following way as a matrix equation. This matrix is acting on X to give Y, where Y is this partition function that we have here. V is this matrix, which has genus and R prime as the indices, and X is another vector, which is that sum over characters. So I just reproduce that expression here. What we see is that this V matrix is actually a van der Waals matrix with integer entries. So dimension of the representation divides part G, so it's an integer matrix. It is a van der Waals matrix. It's invertible because for every R prime, this factor mod G over dr prime is different because R prime is a sum over representations with different dimensions. So it's an invertible van der Waals matrix, so we can invert it to write X in terms of this is the definition of X, and then we can write this as V inverse acting on Y. And because V is an integer matrix, V inverse has rational numbers in it. Y is the partition function, which we already know is rational. So this sum of characters is rational, from which we know the full sum over all representations, which is just a sum over R prime, sum over R for each R prime. This is also an integer. So this is a QFT way of rephrasing result in character theory that sum over all representations for the characters is an integer. So this is a result for column sum. But we can also have row sums, which is a sum over conjugacy classes. For example, if we take we sum over conjugacy classes of representations, this is a row sum in the character table. This is also an integer. So how do we see this from a quantum field theory? So this is like the dual statement for conjugacy class. To see this, we have to look at, so the question is, can we interpret this in a quantum field theory? For this, we actually introduce a new topological quantum field theory, which now depends on the representation ring of the group. So if we have a representation ring, you can put multiplication on it, which is this mu that we have here, which is just given by tensor product of irreducible representations and is decomposed in integral sets. We also have this G, which is a non-degenerate bilinear form, and we can make RG into a Frobenius algebra. So this defines a new TQFT. And this TQFT, again, we can construct all the partition functions, etc., for this TQFT. So this assigns the vector space RG to the circle. So similar to how the center of the group algebra is assigned to the circle in the G TQFT. And we can compute the general partition function for a genus G manifold with boundaries. Now the boundaries are labeled by irreducible representations, analogous to the conjugacy classes that we're labeling boundaries in the G TQFT. So for this, we can compute the partition function and we get this expression. So this is the analogous statement for the GTQFT. And again, we see that this is actually a rational number, which we can find again by the prescription or by acting on it with the Galois group on this expression. Now we use the exactly similar method in this TQFT to prove the integrality result for columns. So again, we split the sum into two sums like this, where now the sum here is split according to the dimension, the number of elements in the conjugacy class instead of the dimension of the representation. And we again realize that this partition function here can be thought of as a matrix acting on X. So this matrix acting on X giving Y. Again, we have a Van der Waals matrix, which is invertible, and we can invert that matrix to get Y in terms of to get X in terms of Y. And we see that because again the Van der Waals matrix is integer, we see that this combination is an integer. So this combination is a rational number, but characters are algebraic integers, so they have to be integers. So this combination of characters, which is defined here, is an integer. So the full sum of our conjugacy classes also is an integer. So this is the row sum version of the column sum result initially. And we have these two TQFTs in the picture, G TQFT and RG TQFT, which are the two TQFTs that we need to use to prove these row and column results. But we know that this is a special example of an integrality result. There are many, many such combinations of characters which are integers, which are valid in integers. And the question is, usually we use Galois theory to essentially find those combinations. And one would like to interpret that Galois theory argument in the TQFT way. So is there any questions so far on this?
So to give a two-dimensional TQFT, it's sufficient to give a Frobenius algebra, right?
Yes.
What you're saying?
A closed two-dimensional TQFT, which, yeah. If we have corners for the manifold, well, then also you just, in the semi-simple case, we just need modules over this Frobenius algebra. There is some discrete choice to be made, but essentially it's the Frobenius algebra that defines. Okay. So let's look at the Galois action on character table. So given the character table of a group, we can consider the minimal field that contains all the elements of the character table. And that field is contained in the cyclotomic field, which is defined by the exponent of the group. It's a minimal field is often a subfield of the cyclotomic field. And we can act with the Galois group of that field on the characters. And this action, sigma acting on chi r g, can be interpreted as, can be seen as a permutation of the irreducible representations, which is here. So there's some abuse of notation here. Sigma acting on this character here, we are thinking of as a permutation of the irreducible. Or we can think of it as taking g to a power sigma, where sigma is now a number co-prime to order of g. So we can either think of it as something acting on the conjugacy classes or something which acts on the representations. Both actions is just a permutation. So we have this action of the Galois group. And given this action, there are many integral combinations that we can find. In fact, any sum which involves a full orbit under this Galois group action will be integral. So this immediately gives us lots of combinations of characters which are integral. And the question is, how do we interpret this in the world of TQFT? So to understand this, we have to look at a notion of symmetries for these TQFTs. So 2D TQFTs, as we saw, is defined by a Frobenius algebra, and we have to define a symmetry for these two-dimensional TQFTs. And this was looked at initially, but in this paper, I think one of the authors is here, and also Bharadwaj, Sakura, and Jingjiang Wu also looked at symmetries of 2D TQFTs. Essentially, it's an action on the Frobenius algebra such that this multiplication and this non-degenerate binary form are preserved. So because we are dealing with semi-simple algebras, we also always have a basis of idempotent. So in this idempotent basis, suppose Pi is the idempotent basis. In that basis, the symmetry is just a permutation of the idempotence such that this theta is preserved. So theta is just a trace of the Frobenius algebra for these idempotent elements, or the G actor on these PIs. So that should be preserved. So this is the definition of a symmetry. Physically, these thetas will be just one-point functions of operators, And this is just saying that this permutation permutes the local operators in the QFT, but preserves the one-point function, which is the usual notion of a symmetry of a quantum field theory. So with this notion, we can now look at how Galois group can be seen as a symmetry of a two-dimensional TQFT. So we saw that we have this action of the Galois group on representations through permutations. That action gives us a permutation of these idempotent bases for the center of the group algebra. So the center of the group algebra has an idempotent basis labeled by irreducible representations, that is this PR. And there's an action on this given by the Galois group. And the theta for these PRs is just dr square over mod g squared. The permutation by the Galois group preserves the dimension of the representation. So this preserves the theta. So this is a symmetry of the two-dimensional TQFT. So the Galois group acting on this G TQFT in this way is a symmetry. Completely analogous to this, we also have a conjugacy clause labeling the idempotence in the RG TQFT. So we again have the Galois group acting on the conjugacy classes is a symmetry of the RG TQFT. So there are these two kinds of symmetries that we have for these two special TQFTs. Any questions on this?
Level of Frobenius actions. This is
Sorry.
what is this on the level of the Frobenius algebra? Just an action, group action on.
Yeah, it's a group action which preserves the Frobenius form. Yeah. So now we can look at the vector space associated to a circle. Usually, physically your theory is a unitary theory. There's some Hilbert space, and the center of the group algebra, which is associated to the circle, is a Hilbert space. And we have some states in the Hilbert space, which can be written in this basis of idempotence, these PRs. And among those states, there's a special set of states, which we just call Q states, which just means that the coefficients that show up are just rational numbers. So there's a state in the Hilbert space of the theory. Now, if we have a Q state, which is invariant under this Galois symmetry, so we thought of Galois group action as a symmetry. If you have a state, Q state, which is invariant under the Galois symmetry, so this is a sigma acting on psi is just acting on the idempotence to the sigma. That's the definition of the symmetry. If it is invariant under the full Galois group, we can replace this PRs with chi-Rs. So we go from an operator to an algebraic expression. That combination is also invariant under the group, because chi and p both get permuted in the same way under the Galois group action. So we can go from a state in the Hilbert space to a combination of characters. And the fact that this is completely, this state is invariant under the Galois group action means that this combination has to be rational. So this is the statement that we get.
You're saying Galois group, but isn't G just an abstract group?
Yeah, so the G that defines the TQFT is a general finite group. The Galois group that we're acting with is a particular one that comes from the character table of the G group. So we take the character table and we just find a cyclotomic field containing the character table. Yes. So every G invariant, every Galois symmetry invariant state corresponds to a combination of characters which is rational. And if these alphas are integers, then that combination is always an integer. So this is how you can associate certain states in the theory to combinations of characters which are integers. So we also do some refined integrality results. Essentially, we look at certain other combinations of characters which can also be proved purely using partition functions without using Galois theory. For example, to prove this, you have to use certain partition functions of that type. We have to consider torus, and there are many boundaries for that torus. And we can use that partition function and again do this van der Monde matrix method to prove that this combination is integral. We can prove that this combination is integral using another partition function. And we expect that all the integrality results that you can get from Galois theory can be proved using partition functions. So in view of time, I won't go to the details of these two. I just wanted to mention that these can also be proved. So let me conclude by saying that correlation functions or partition functions of two-dimensional TQFTs can be used to prove integrality results. And this GTQFT allows us to prove integrality results for column sums and RGTQFT for the dual results for the row sums. And the Galois action on the cat table can be interpreted as a symmetry of these two TQFTs. And this natural question about extended two-dimensional TQFTs. So far, we looked at closed TQFTs. Extended versions have corners. There's more, slightly more data in them. So it will be interesting to see what this extended TQFTs tells us about integrality and in general number theory for character. Okay, I'll stop here. Thank you.